Well, thanks for coming to our first research talk at the center. This is actually, we consider this as kind of an experiment, and it's a great honor and pleasure to have my mentor, colleague, and friend for the last 24 years be our first speaker here. It's Lezung Chan, that's my best pronunciation of his name, who's currently at the Abdus Salam International Center for Theoretical Physics in Trieste, Italy, and he will talk to us about something that I think he knows something about, equisingularity problems.
Well, thank you for coming, and I feel a bit, I would say annoyed, but to do the first lecture of this series of lectures. I'm going to talk about equisingularity problems, not because I have anything new to say about it, but because I am feeling that I will very soon not have anything to say about it. So, and I think that these type of problems have been defined, or I don't know if you can say defined, but they have been introduced at least by Zariski about 40 years ago. And myself, I was introduced to this type of problem by Hironaka himself. And Hironaka was a student of Zariski. So the problem is very simple, because the way to state it is a very simple way. If you have two singularities, in terms of mathematics, it would be any local ring. For mathematicians, since you have a lot of local rings, if you look in my way, should look at a complex analytic local ring. If you look it as an algebraist, you look it as an Arthurian local ring. Maybe it should be equidimensional, and anyway it will be on the ring of complex numbers. And if you want to look at the geometry, you take a complex analytic space, and you take a point on this complex analytic space. So the germ of the space at the point is more or less equivalent to the data given by the local ring. So this should be a singularity. And you want to decide when two singularities, so two objects of these types, are in some ways the same. When are they the same? So this formulation is vague because it doesn't have a clear definition. And Zariski gave only a clear definition in one case. He considered a kind of complex analytic local ring of dimension 1. And he decides that two of these rings are the same if and only if they have the same saturation. I'm not going to speak about saturation rings, but you can find it in a series of papers by Zariski called the Studies in Equisingularity. It's in the American Journal of Math. And they have been published between 1964 and 1968, I think, is 1, 2, 3. And then afterwards he made a series of papers called Global Theory of Saturation, also in American Journal of Math.
You said this was only for curves?
1, 2, 3. Is, roughly speaking, is for curves. So
here by same you mean isomorphic and isomorphic?
yes, isomorphic.
No.
So let me tell you what we.
I mean the saturations are isomorphic, is that what you're saying?
Yes.
Yeah. The bottom rings are not isomorphic.
No, these ones they are equisingular if and only if
That's
the saturation are isomorphic. And this was, so let me tell you what we know about this. We know that if you have two local rings, we say we can speak about the normalizations of the rings. And the normalization of the rings, you can view them as the meromorphic functions. Meromorphic functions which are bounded. So if you look at all the meromorphic functions on your singularity which are bounded, then you can speak about the normalization of the ring. So between the ring and the normalization, you have another ring that you can call the saturation of the ring. And they are the meromorphic functions which are Lipschitz. So this formulation was given by Pham and Tessier. This was in 1970. I think it is in the Nice Congress of Mathematics. And so having the same saturation would mean exactly that these rings are the same. So we in some ways around the years 1968 to 1971 about we made a very strong research on that topic, and this is one of the very important results of Pham and Tessier. I don't know how far this is known, but this is the result we obtained. And so you have the following formulation. So in dimension 1, you have that equisingularity on one side. Second, you have same saturation. Then there is a result by Zariski which says that same saturation is equivalent to the fact that you have the same topology. So let me describe what is the same topology. If you have two plane curves have the same topology. If you look to the knot defined or the link defined by each of these singularities, and the links are of the same type. So you have here a link, eventually several components, and they have of the same type. So you have define it by topology, so they have the same type. And this means the same links. The same link means the same knots. So it means each knots are the same, plus pairwise linking numbers.
That's only for plane curves?
Yes.
Number 3, but the other two are in any embedding dimension?
Well, I don't remember very well the definition of the saturation ring, but I suppose you need some particular hypothesis. They are related to the dimension of the singular locus, so it's roughly speaking like family of curves or curve. You see.
But there might be space curves that
Yes.
aren't embedded
Yeah.
all in the plane.
Yeah, something like that.
Also about the link. the link actually requires some geometry. I mean, clearly if they have the same link inside where they hit a sphere, then they have the same topology. But if they have the same topology, I think Trotman has told me it's actually hard. That then in fact, they have the same link when you intersect with a sphere. Right? Knowing that there's an open set with this, where you get the cone on this, and an open set when you get the cone on this isn't the same as saying, anyway, is that?
This implies this, obviously.
That's certainly true.
There's a contrary. The contrary in general is not true.
Yeah, I thought Trotman told me somebody proved something.
For this type of links coming from plane curve,
Yeah.
this is true.
Okay.
Okay, so in that case it is true. So that's very special, what we call it here. So this plane curve. The fourth is quite, it was proved by Zariski also. You have the same resolution graph. So let me explain you what is the resolution graph. So it is known that if you have a singularity, now if you blow up this point, and you blow up the points above these points which are singular or which are tangent, so you make appear like that a tree. And the tree comes together with some multiplicities, because when you blow up like that, you have the multiplicities coming from the curve. I don't explain because either you know, this is easy. If you don't know, you have to think about it, and then you find after a few days that the tree comes with some multiplicities. So you create like that a graph, and the graph has only normal crossing after some times because you have killed all the singularities, and then the fourth condition is the two resolution graphs are of the same type. So you have the same type of resolution graph. So this is very strong, and this is given by Zariski. And you can say even more.
We'll say more supposedly.
Yes. You say you have same multiplicities and same resolution graph. Okay. And so that's what was known by Zariski somehow in 1968. And Hironaka said in his seminar in 1968 that eventually, if you have a family of curves, of plane curves, and now you assume that in this family the Milnor number is constant, then this should imply you have this equisingularity. So that's my Hironaka. So in 1968 he thought he has a proof, and we saw in 1969 that the proof was not correct. And then I gave a proof of that in 1971. And then with Ramanujam, I proved that this was true for hypersurfaces for the dimension not 2. So what is the relation of this this question with the question of Hironaka? Is in fact that there is a fifth condition by Zariski, which says that if you if you project the curve on a line, then you define what is called the discriminant. And he assumed that the discriminant is constant in a family. Then he obtains about the same result. He gets equisingularity. So the discriminant is given, in fact, by a formula. It is given by Milnor number plus the degree of the extension, -1. And he proves that if this number is constant, then not only Milnor number is constant, but the multiplicity is constant. So somehow equisingularity implies Milnor constant. And because of this proof, I show that equisingularity implies also M constant. So in that case, it means multiplicity constant.
When did Zariski ask his multiplicity question?
1969. Okay, so it means only that the general problem of equisingularity seems to be very clear for the case of plane curves. And there are many formulations, and I am not going to give all the possible formulations about these conditions, but you can see that these 4 first conditions, they can be stated for 2 different singularities, but the 5th conditions and this equation of Hironaka can be stated only for families of plane curves. So that's a difference. For instance, if you study family of projective curves, non-singular projective curves, anybody knows that the degree gives you the topology of the embedding. But question, how is the embedding? And I don't know that there is a topological answer to that question. So it is easy to say something is constant in a family, but it is difficult to describe what is each object. So that's a general problem. So these type of problems can be solved in a family, but we don't know what the elements of the family are. When these type of questions are stated for different singularities. Okay, so all these questions were related to another type of results, in fact, which appears about the same time. There were research done by Whitney and by Tom, which were looking, in fact, to the same type of problem in analytic space. So I'll just draw you an analytic space. So you see in this picture you have 3 types of points. This point.
There's some colored chalk if you want.
Yeah, this point here. You have also these points here. And inside, and here the non-singular point. So you have 3 types of points, roughly. And they correspond to pieces of the analytic space, which corresponds to a stratification of the space. So if you take a space here, you stratify your space, means you have a disjoint union by manifolds. So since I consider complex manifold, a complex analytic space, I have complex manifolds, and this gives you a disjoint union by these manifolds, and you ask this disjoint union to be locally finite to avoid to have a disjoint union by points, for instance. Okay, and you ask that this union is made of points of the same type. So each of these points, same type. So Tom and Whitney looked to this question. In fact, Zariski also knew about the research of Whitney and Tom, but the research of Whitney and Tom was for real type of spaces, and they came to some conclusion which relate to the problem of Tom, at least in the case of codimension 1 hypersurfaces. So you have stratifications. So there's a disjoint union of complex manifold, locally finite. And they satisfy a condition which is the following, that if X alpha is contained in X alpha intersect X beta, X beta bar, then this implies X alpha belongs to X beta bar. This is called frontier condition. You want to avoid, on a situation like that, you want to avoid that you have a stratum X alpha here and a stratum X beta like that. So you want to avoid that two objects are transverse like that. So you ask this type of strange conditions. Okay, so Whitney obtained what is called Whitney conditions. Whitney conditions is a very strange conditions. You say that X beta has Whitney condition along X alpha if you have the following thing. For any sequence converging to a point of X alpha, and for any sequence of X alpha converging to Y. So you can always extract a subsequence so that the tangent space has a limit. And you ask also the lines has a limit. And you ask this. And you ask this for any pair X alpha, X beta with X alpha inside X beta bar and any Y of X beta. So it's a strange condition. You can forget about it because it's somehow is a condition for topologists, and And it has triggered a lot of research in the next 20 years, maybe. And all of a sudden, everything stopped. Okay. So if you want to express the results of Zariski in these terms, it only says that if in a family of plane curve you have delta or mu constant, so the family along this line of singularities satisfies Whitney conditions. It's equivalent. Okay, so that's somehow the relation. So it appears that maybe the Whitney conditions were interesting, because the Whitney conditions gives you the topological triviality, gives you a lot of things that people needed for topological reasons. So Whitney conditions. Triviality. So people thought about this, and particularly Tessier has thought about this. And he obtained a very nice criterion to study this criterion, to characterize Whitney conditions. If you have an analytic space, complex analytic space, you can project it on a linear space. And you take this X to be equidimensional. I asked this to avoid some particular hypothesis. So I suppose maybe I have several components of X at this point X. Maybe you have several components like that. But I want all the components to have the same dimension. And I ask K to be between 2 and the dimension of X plus 1. So if K was dimension of X plus 1, a generic projection is kind of embedding somehow. Okay, so the discriminant of this projection is obviously the image of X. And the generic fiber is empty. But on the contrary, if I project on the plane, so I have to project in a nice way, in such a way that the fibers are exactly dimension of X minus 2. Okay. So if you think about the discriminant to be the points where the fibers are non-singular, so of course, if the dimension of X is big enough, it could be the whole C2. Okay? So there is a very easy way to avoid this. You restrict the projection in the non-singular part of X, and you project on C2. Okay. Now you obtain like that a critical locus, you equal P1. So P1 could be empty, but if it's not empty, it is clear that generically it will be dimension 1. So the closure of this is a curve, and I call it the polar curve. So you can see it like that. I give you an example. If you take, for instance, this is a discriminant of the equation of degree degree 2 is 0.3, so degree 4. Okay, so it's discriminant of the equation of degree 4 is a surface. If I project it on a plane, it's easy to see that all the planes, when you tend to the origin here, are horizontal. So if I forget the singular locus, the projection is empty. Okay, so in that case, the polar curve is empty. But if you take, for instance, this family of strophoid, which gives you this, if you project this strophoid in the plane of the blackboard, so the curve is like that, without this point. And when I take the closure, I have this point. So this is the polar curve. Okay, so it's most of the time this notion is not empty, of course. So it's empty in very special case, which this is a special case. But in general, it's not empty. And so I define for generic projection, so for almost all projection, I define like that a variety of dimension k minus 1. It's called the polar variety of dimension k minus 1. So Tessier shows that assume I have a stratification like that, and assume that for all the points x belonging to x alpha and x beta bar containing x alpha, and assume that the polar varieties, so I have to use of x beta bar at x are constant. So you have to assume this for all x in x alpha, for x alpha containing x beta bar.
You mean they're multiplicities?
Yes, the multiplicities of these along x alpha bar. So you have a family of multiplicities. They are ranging from 2 to dimension of x bar plus 1. You assume all these are constant. So this implies Whitney conditions. Okay, so once you have that, you can prove a lot of things. I will say some of them later. But the result of Tessier is weak for the following reasons. It's not algebraic. Or the statement is vaguely algebraic. It's not algebraic in the following sense: is I know that pk exists, but I don't define it algebraically, because I have to define it for almost all projections, and I have to define at least the multiplicity for almost all projections of this priority at the point x. And I know that Kleiman has tried many years to find something, or I think Gaffney also, but I don't know if you have obtained a precise result about this algebraicity of this. I'm not sure about this. Anyway, so that's we have to get the result of this. And this is not very clear. This is clear in geometrical terms, but it is not clear in algebraic terms.
So wait, did your face mean you do or don't have a nice algebraic characterization of polar multiplicities? I saw your face, I just didn't know what it meant.
I don't know that I've worked on it. Have we, Terry, have we worked on this?
Not together, no.
Sorry.
It also depends on what you mean by an answer. You know, what an
Well, I have a
answer
local
would be.
ring. I have a local ring. And the question is the following.
mean,
I have a local
if it's
ring.
a local ring. I could look at the Jacobian module. I could look at the minimal reduction
Yeah, but
of
already-
the Jacobian module, and that would give me my zero-dimensional invariant.
Already,
Is that algebraic enough
already
for
the
you?
Jacobian module is not defined in terms of the ring. I have a ring. I have only algebraic tools from this ring to go and obtain the multiplicities. I don't have that. See, that's
You don't have Jacobian ideals either, then, I was.
yeah.
Why not?
As I said, it depends
You
on
want to-
what is the framework.
You
When the
want to-
question is answered, depends on the framework of what he would accept for an answer.
Right, but
This is a
you're
discussion better
concerned
than-
about the embedding of the ring? And if you start with an algebraic ring, you have an embedding, and then you can form the Jacobian module.
Yes, but
All these multiplicities, they're certainly well defined in the algebraic case.
you mean that you can embed this in some.
But if you start with something algebraic, it's not algebraic to begin with, then the question doesn't.
No. I mean, I start from that ring. I mean, I'm given.
Well, from
But
An
I know I
NIT
started the conversation, but maybe
Okay.
this is a long, that's something I should have asked you at the end of the talk.
Sorry.
My mistake. I thought it was a yes/no answer. I'll ask you at
Another type of conditions we were interested in, something I did with Tessier, is instead of looking at the polar varieties, we look at the limit of tangent space. So if you take any singularity at a non-singular point, you have a tangent space. And we look at all the hyperplanes. So this is embedded in some Cn. And I look at all the hyperplanes containing this tangent plane. So it's a lot of hyperplanes like that. And I look at all the possible limits of these hyperplanes when it tends to x. So we obtain a kind of strange result, which is the following. Associated to this x, we can define the tangent cone. And of course, all the tangents to the tangent cone are limit of tangents. That is something you expect. But there are some small subcone. So all the hyperplane containing a tangent to these subcones is also a limit of tangent. And you can show that these tangent cones are tangent cones of these polar varieties. Okay, so you have all this family of subcone, and these subcones are exactly these ones. And then all the limit of tangent hyperplanes are tangent hyperplanes to the tangent cone, then tangent hyperplane to small cones, and so on. That's what we call the aureole. So you can define like that the limit of tangent hyperplane. Now, if you have such a decomposition, so that for all these, I don't ask this anymore, but I ask these aureoles are behaving as a family along X alpha. The aureole of X beta bar is a family along X alpha. I don't define this precisely, but it's quite precise, in fact. Then this implies you have the Whitney conditions. So it's very strange. Now you instead of approaching the Whitney conditions through the polar varieties, you approach it through the limit of tangents, which is inspired by the Whitney conditions. Then you also have the Whitney conditions. Okay, so and so this tangent cone is well defined again by algebraic constructions, and I don't think this is well defined still.
I won't ask this time.
Okay. Okay. Anyway, so this is something, and now there is another characterization by topology. Instead of looking at these multiplicities here and to the you look at the generic fiber of this. So you can define the generic fiber is just the fiber which is not in the projections of the polar curve. So it has an Euler characteristic. So for each of these projections, I have the Euler characteristic of the generic fiber.
Are we looking inside a closed ball or globally?
Yeah, locally.
Okay.
It's locally. Everything is locally at X.
Yeah.
I don't write the balls.
Yeah,
but
that's
it's something obvious.
Yeah.
Now, I have a family of these Euler characteristics. Is from K is from 2 to the dimension of X plus 1. So again, if this family is constant along X alpha for all X beta bar, then this stratification satisfies with my condition. So it's for topologies. So you can really characterize it through purely topology. So again, I don't know this Euler characteristic can be characterized purely algebraically. It should be characterized purely algebraically, but it's not. I suppose that you can do it with your Jacobian modules, but it has to be systematic in some ways. Okay. So once we finish this type of work, it's clear that we have a kind of notion of equisingularity on a space, which is characterized by all these conditions. But then what we obtain is Whitney conditions give you the equisingularity. And as I say, the advantage of this situation that you have something which will imply the topological triviality. But you cannot answer, for instance, the following questions. That was a question of Zariski. Zariski was not happy with the Whitney conditions, because the Whitney conditions, of course, contains the same multiplicity. I say it's of course because from all this characterization you obtain somewhere the multiplicity. But Zariski wanted to define equisingularity, at least for the complex field, as at least implying the same topology. So equisingularity that I didn't define, except the case of dimension 1, equisingularity should imply same topology. So the question of Zariski was equisingularity should define at least same multiplicity. But he didn't define equisingularity, so he asked the question for this implication. So do you have same multiplicity if you have the same topology? And this we cannot answer even if you have a family of surface with the same topology, if equisingularity of the family implies same multiplicity. So we don't know how to answer this. Okay. So, in fact, here we have Whitney conditions, equisingularity, that we don't know what it is, same topology. You have map like that. You have a tentative map like that. And you should have a map like that. Okay? But we don't know anything about this. So you don't know how to answer because you don't know a right definition of this object. But what we obtain is same multiplicity. And at least this should be true.
morally, I don't see why equisingularity should necessarily imply same multiplicity. Why should whatever you mean by being equally singular mean same multiplicity? What you get by intersecting the number of points that you get in some generic intersection. Why morally do you necessarily want that? Yeah. It doesn't bother me to have it.
Yeah, it bothers. It is bothering because there are some hints. Let me tell you. In the case of hypersurface, we can obtain the multiplicity in the following way. If you take the generic fiber of the hypersurface, this one, and you make it turn around the zero of the hypersurface. So you have the monormy of the hypersurface. So you are tempted to look at the iteration of the monormy a number of times given by the multiplicity. And somehow, in most of cases, this is non-trivial. This has this has a
nilpotent part.
yes. But in some case, this doesn't work. So we expect that M only depends on the monormy and the monormy only depends on the topology. So you should find the M as some invariant. But if the Euler characteristic of the tangent cone is bad, it doesn't work. So so that's a kind of vague reason for hypersurface. So at least later on in his life, Zariski weakened his conditions, and he asked this for hypersurfaces. Because anyway, he didn't hope in the general case that this would imply this. Okay, but so in some sense you can ask equisingularity. Equisingularity should mean that some invariant which has what I used to call now topological invariant is not an invariant which depends only on the topology, but which is upper semi-continuous. So it will be constant on the open Zariski-Nernst set. So of course, this type of invariant is not topological in the usual sense, but it is roughly better than the nanitic invariant, which is continuously varying. So if you look in these terms, then you have an equisingularity for any type of upper semi-continuous invariant. Okay, so you can call equisingularity for multiplicity something which you define equisingularity only by equimultiplicity. But you can also define equisingularity by all the type of invariants I have defined, like the Euler characteristic or the tangent cone or the limit of tangents and so on. But so it means that to get the right definition of equisingularity, you don't have a right definition as Zariski looked from the beginning, but maybe each time you have a kind of topological-like invariant, you have a notion of equisingularity. And then it gives you that invariant should stratify your object in a very nice way and so on. So it depends exactly what you want to ask. Okay, but then related to what I say, the notion of equisingularity is related to define the right invariant to stratify a singular analytic set. But of course, in this case, I never talked about a real analytic set. In the real case, it's even more complicated because the real case, you have invariant in some part and empty set in the other part. So it's more difficult. But that's what I say, that coming to this stage of thinking, I don't believe that there would be a theory analogous to the saturation theory of Zariski, which is nice, but it is more or less given by the Whitney conditions. But I would define equisingularity related to one or several topological-like invariant. And then this is one of the questions you can have in the between. So I don't know if it wakes up some research in this topic, but I just want to mention that even if we stopped researching in that about nearly 20 years now, I don't think that the research should be stopped like that, because a lot has to be done in that direction still. So, thank you.
All right, let's. Are there questions? We have lots of time before we have to walk 5 feet across the street to dinner.
Is there any hope, do you think, of really getting the same level of understanding that Zariski got for curves in more complicated situations? I mean, one of the things that Zariski did, of course, was he was able to study these things without putting them into families. So that's what I'm getting at. So are we going to be restricted to just looking at families of things?
My answer is depends on the degree of algebraization of the theory. When I thought about this, I thought about this about a year ago again, and I realized that most of what has been done is not really well algebraized. So as long as it's not very well algebraized, I cannot really answer. Because it's surprising that Zariski, I don't know how he did it. This I didn't ask him, in fact. But he reached very quickly a very nice algebraization in the case of curves, plane curves. But he never really thought in more complicated situation. And in more complicated situation, I remember how Tessier did his way and how I did my way, and how we meet for a few questions together. And in those days, we were so keen to find the result, not really to find a good way to get the result. So that we just went directly to the point. But now when I think of it, because of that, people didn't look, except maybe Steve, but people didn't really look to a way to look on any field or field of characteristic 0 and make something purely algebraic. And I think we need to think in a more algebraic way.
For algebra.
No, that's true. I mean, once you did the geometry, it's okay, but you have to bounce in the other direction. So I'm a bit harsh on the algebra, but for instance, there is one case, remember that when we discovered this Bhattacharya polynomials, we looked at kind of Samuel type of polynomials in two variables for products of ideals. So if you take a product of maximally ideal like the Jacobian ideal, and you look at the length of this quotient, and you obtain now a polynomial in two variables. So the terms of highest degree, they would give you the min for instance for isolated singularity of a hypersurface. It would give you the Milnor number of the different sections of the hypersurface by different linear space, and for generic linear space. So in that case, we were happy because we obtained an algebraization immediately. But we stopped there. We didn't go further because this was only for the case of isolated singularity. We never cared of looking at non-isolated singularity, for instance. Because in the case of non-isolated singularity, you have to deal with some quotient which gives you something of finite length. So we never thought of this, really. So, I mean, we were not so much algebraized, much more geometer than algebraized. So,
We haven't said anything about resolution of singularities, though. It's certainly one of Zariski's.
yes, but the resolution also gives some limitation that we thought about equisingularity by equiresolution. But Tessier killed the thing by saying that if you have equiresolution, you have Whitney conditions. So we didn't know what to answer to that. I mean, it means you obtain something which is kind of stronger than Whitney conditions. So.
Well, another reason for considering equisingularity is to stratify the space to give you loci to blow up to resolve the singularity.
Yes. That was one of the reasons. At least it was Hironaka's reason to look at this.
But, goes back to the 19th century.
Yes, of course. But for instance, Zariski defined equidimensionality type for singularities, and he defines something which looks like equisingularity, but he stratifies spaces, and he gives you equidimensionality type for a given singularity on some space. And this, of course, the research about this was not done properly. It's stopped about when Zariski died. Nobody. I remember I looked at it and I had some ideas and I gave up. So you see, when a master like him disappears, I mean.
You mentioned the reals at the end. I should know this, and maybe Terry's the right one to ask, but reasonable notion of polar varieties over the reals?
Yeah, you
Do
can
polar
define
multiplicities control anything over the reals, like Whitney conditions?
No, you can define polar varieties in the same way I do in this case.
Does it give you anything worth having? Does it give you any results that are worth anything? Do Do you get some upper semi-continuous invariance that's stratified?
I think you can do something.
It should be a real integral closure thing, I would think. No?
Yeah, I think it's more complicated. The nice thing about the complex case is the results are written only if,
Yes.
I don't know if you maybe can use.
The reals, it depends on the way you project. So
Well, it does in the complexes too.
There's also the question of what the right equisingularity condition is in the real. If you use Lipschitz equisingularity, then maybe possibly get stronger results from just using Whitney, in the sense that Mount does his results about, if you only have the Whitney conditions, then invariance can vary in a sort of continuous way with the Lipschitz conditions.
Well, it looks like some people need to leave. Maybe we should thank the speaker again and then let people leave who need to leave. And